recording. I'll have an assignment for section 2.6 listed after class. That'll be on the website. Anyway, that's due next Thursday at 9 p.m.
Can you share your screen?
Oh, yes. So I have something listed for section 2.6 after class today when I send you, the usual email that I do. And tonight, what do we have? Don't forget to hand in the assignment for section 2.2 and the web assign for 2.1 and 2.2 is due as well this evening. All right. So yesterday we had a few. So the sections are a little kind of short. These last few sections. So we went over 2.4, just talking about the average rate of change of a function, just the basic sort of definition of what that is. And here we have a few problems to look at. So which ones did I assign? 18 and 38. So number 18. So something like number 18. And which ones were assigned? 7 to 25 odd. So number 17. So we have f of x is equal to x to the third minus 4x squared. Find the average rate of change from x equals 0 to 10. So we have the interval from 0 to 10. We're looking for the average rate of change. So that's just going to be equal to f of 10 minus f of 0 over 10 minus 0. So f of 10 is 1,000 minus 400. Oops, 1,000 minus 400 minus f of 0 is 0 over 10. So 600 over 10, so it's 60. Okay? So, problem 18 is just like that. You've got a function, you've got an interval for t, and they're asking for the average rate of change. Do watch out for sign errors, mixing up your positives and your negatives. So in number 18, like one of the values on the interval is t equals -2 to t equals 2. So here f of t is equal to t to the fourth minus t to the third plus t squared. So find average rate of change. On the interval from -2 to 2. So let's find the average rate of change on the interval from -1 to 1. So that's going to be f of 1 minus f of -1 over 1 minus -1. Right, so, be careful of the sign errors here because you're combining a lot of, negatives together. So a negative times a negative, of course, is negative, and negative times negative is positive, or negative times negative is positive, and negative times negative is negative again. So be careful for that. So f of 1 is 1 minus 1 plus 1 minus f of negative 1. Negative 1 to the fourth is 1. Minus, so here's where a sign error might occur. Minus negative 1 to the third. Negative 1 to the third is negative 1. And then negative 1 squared is 1. And this is 2 on the bottom. See that? So it's especially here when you're plugging in negative 1 into t to the third, okay, that turns out to be negative 1, but you're subtracting it. So it's minus 1. So there's quite a few, not to mention the fact that there's a minus out here. So there's quite a few minus signs floating around, so, be careful of that. So this is 1 minus, and this here is 3 over 2. So minus 2 over 2 is minus 1. Okay? So in number 18, you're supposed to find the average rate of change from negative 2 to 2. All right. And then in the last few problems, we've got... So when you're talking about average rate of change, you're talking about usually talking about various physical situations or situations in which the rate of change makes some sort of sense from a practical perspective, from a physics or an economic or whatever perspective that you're looking at. So I assigned number 38, which is the classical setup for average rates of change, or for rates of change, which is the rate of change of distance over time, which of course is speed. But let's do another one like it. Okay, number 32. So in number 32, so before we even start, if f of x or f of t is in units of distance, so for example, let's say meters, and t is in units of time, so let's say minutes, then the rate of change f of b minus f of a over b minus a is in, right, distance over time. Right, in this case over here, meters per minute. And distance over time is often thought of as speed. Can often be thought of as speed. Not always, but, often. So as long as you're traveling in a line, you're not sort of turning around and reversing, then distance over time can be thought of as speed. If it's, if you're driving forward and then coming back, stopping and then coming back, then distance over time and speed, don't quite match up. But as long as you're sort of traveling in a straight line, then it's speed. So in number 32, we have the following data. So a man is running around a circular track in one direction, apparently. And the circular track is 200 meters in circumference. An observer uses a stopwatch to record the runner's time at the end of each lap, obtaining the following table of data. So we've got distance in meters, and time. All right, so somebody's timing their splits going around this track. Of course, the track you run on usually isn't a circle, but an oval in shape. So 32 seconds. So time is in seconds. So 32 seconds, 68 seconds, 108 seconds, 152 seconds, 203, 263, 335, 412. And the number of meters is 200, 400, 600, 800, 1,000, 1,200, 1,400, and 1,600. So the distance traveled in 32 seconds is 200 meters. In 68 seconds is 400 meters, so on and so forth. Okay. Part A asks, what is the man's average speed between 68 and 152 seconds? So average speed. So in this case, that means average rate of change, right? Distance over time is distance over time. The average rate of change is in units, distance over time. So we think of that as speed. So average speed over the interval from 68 to 152. So after completing 2 laps to completing 4 laps. So the third and fourth lap. So the distance traveled is 800 minus 400, right? So the distance traveled at 152 seconds minus the distance traveled at 68 seconds over 152 minus 68, right? So this is 800 minus 400 over, so 152 minus 68, so 84 over 84 seconds. So we have 400 over 84, which is approximately equal to, where's my calculator? There it is. So 4.76. And the units here are meters per second. Okay, so 4.76 meters per second. That's his average speed. Now, of course, at any one given moment, his speed could be more or less than that when you think of speed as an instantaneous measure. But in order to define that notion of instantaneous speed, that takes calculus, the notion of a derivative in calculus. All right, point B, part B. What is the man's average speed between 263 and 412? So 263 and 412. So that's that's 2 laps, yeah. So average speed from 463 or 263 to 412. So that's D of 263 minus D of 400, or sorry, the other way around. 412 minus D of 263 over 412 minus 263 is equal to, so in this case, it's 1600 minus 1200 over 412 minus 263, so 149. Right, so 400 over 149, which is approximately equal to 2.68. 400 divided by 149. Yeah, 2.68 meters per second. So over these two laps, over these 400 meters, he's going quite a bit faster than he was before. Or sorry, quite a bit slower than he was before. All right, part C. Calculate the man's speed for each lap. Guys, if you give me just a second, I'll be right back. Sorry about that. Okay. For C, calculate his speed for each lap. Well, I mean, I'm not going to do that here. Well, I guess we could do it. Shouldn't be too bad. Let's see. So calculate the speed for each lap around the track. So the first lap, right? So apparently he's starting out at time 0, right? So the first lap is 200 meters minus 0 meters over 32 seconds minus 0 seconds, right? I mean, starting out at time 0, and he hasn't traveled at all. So 200 over 32. So 6.25 meters per second. Second lap, well, each lap is 200, of course. 200 over 68 minus 32. So 200 over 36. 5.55 meters per second. Third lap, again, he's gone 200 meters. How many seconds? 108 minus 68. So this is 40. So 5 meters per second, and so on and so forth, right? So, he's slowing down the first 3 laps, starting at 6.25 meters a second, 5.5 meters a second, 5 meters a second. So these are his average speeds over each lap. So in number 38, it has a graph of 2 distance functions. So here, in number 32, the distance function is given in this table form. So you have less information about the function itself. You just have, so many discrete values for t, and then so many discrete values, corresponding values for d. So that's, not the, so that's less information than you might want for a function, but that's the data you have. In number 38, you've got graphs of 2 distance functions, distance functions over time parameter t. So you've got a little bit more data. And then it asks you several questions about what these 2 distance functions over time. So the 2 speed skaters, A and B, are racing a 500-meter event. And then the distance traveled over time is given to you in this graph. Who won the race? Find the average speed for the first 10 seconds of each skater. find the average speed for the last 15 seconds for each skater. So, similar to what we've done here in this problem. Okay? All right. Let's go back to section 2.5. So we started talking about linear functions. Now, of course, we've already talked about lines geometrically. Now we're going to talk about lines as functions. So a function f of x is linear, representing a line, when it's the form fx equals mx plus b, where m and b are constants. Of course, geometrically, we call m the slope and b the y-intercept. With a linear function, some of these other concepts that we've studied now also correspond to what the m and the b are. So if you have a function like this, so here's a couple examples of linear functions. Given a linear function, f of x equals mx plus b, and any interval pq for x, the average rate of change of f of x on pq is always just the slope. So the slope of the line, in terms of rate of change, is the rate of change. It's a constant rate of change. Right? So we say that linear functions have a constant rate of change. Right? Unlike that problem about the runner going around the track. His rate of change, which in the context of distance over time is speed, his speed is decreasing over time. So his rate of change isn't constant. So a function that models this guy's distance traveled over time isn't going to be a line. It's going to be something else. Also the b, which is the y-intercept, can be thought of as an initial quantity. Sometimes that's what it's called, or initial condition. B in the linear function f of x equal to mx plus b is often called an initial condition. Initial because that's the value of the function at the initial value for x, which would be 0. Value f of 0. So initially, when the problem is starting out, or when the function is starting out at x equal to 0, the value of that function, well, it's m times 0 plus b, which is just b. Okay, so the b, geometrically, we think of it as the y-intercept, but, in a sense of modeling or in a physical or economic situation, we can often think of it as an initial condition. Initial distance, initial quantity, initial, what have you, initial amount. So let's take a look at some problems dealing with linear functions. So number 41 in the text. So now, by the way, in a lot of these problems, there's a lot of sort of not relevant information that's being presented. So you kind of want to ignore that. Well, I mean, you don't have to ignore it, but I mean, we're talking about linear functions. and what you can do with linear functions. So they say in number 41, weather balloons are filled with hydrogen and released at various sites to measure and transmit data about conditions such as air pressure and temperature, period. Okay, well, fine. That's great. But that's not what that's not dealing with linear functions at all. It's just saying, well, we've got these balloons. Nice. So we have balloons, period. So a balloon is filled with hydrogen. I don't know why they're using hydrogen. I think you're supposed to use helium, right? A balloon is filled with hydrogen at the rate of 1/2 feet cubed of hydrogen per second. So feet cubed, so a balloon is filled with hydrogen at a rate of 0.5 feet cubed per second. So that's a rate of change, and they're saying it's constant. Yeah? They're saying it's constant, 1/2 foot cubed per second. Now, of course, it really can't be constant because if you've ever tried to pump up a bicycle with with a pump or whatnot, I mean, it slows down as the pressure inside the tire becomes greater. But whatever. I mean, they're saying in this problem, we're filling up a balloon with hydrogen at a rate of 0.5 feet cubed per second. So feet cubed, right? A foot, that's the unit of length, right? Foot squared, that's a unit of area. And foot cubed, that's a measure of volume, right? So this is 1 foot long. This is 1 by 1 foot square, and this is 1 by 1 by 1 foot cubed. So of course, gas is measured in some kind of volume. So the balloon is filled with hydrogen at a rate of 1/2 a foot cubed per second. Initially, the balloon contains 2 foot cubed of hydrogen. Find a linear function v that models the volume of hydrogen in the balloon at time t. Okay, so part A. So v is equal to the volume of hydrogen in the balloon at t seconds. Right? We know v is a linear function because it says, right, we have that the balloon is being filled at 1/2 a foot cubed per second, and that is a constant, or they're implying it's a constant. So somehow, the rate of change is implied as a constant. So here, v of t is just equal to, well, 1/2 a foot cubed per second. So that's the rate of change. That's the m. Well, let me write it out. mt plus b, where m is the rate of change, constant rate of change. B is the initial condition, the condition at t equal to 0. So here we just have 0.5t plus 2. And that's it. All right, because it's a linear function. B. If the balloon has a capacity of 15 foot cubed, how long does it take to completely fill the balloon? So how long does it take to fill the balloon? So when dealing with questions where quantities have labels, right? T, the label is seconds. V, volume, the label is feet cubed. And then rate of change of V is feet cubed per second. So they're telling you that they want to know when you get a volume of 15. Right? Why volume? Because it says units of volume, feet cubed. So the capacity of the balloon in volume is 15. How long does it take to fill the balloon? So what are they asking for? How long? So what? An answer to what?
Time.
Time, right? So we have 3 units here. We have volume, feet cubed, time in seconds, and rate of change in feet cubed per second. Okay, they're asking you about time. They gave you volume. Now they're asking you about time. So they're just asking you to find T when V equals 15. All right, so 15 is equal to 0.5 T plus 2. Find T when V is equal to 15. Or I shouldn't say when here, 4. Right? I mean, they're implying what they're looking for here. How long? How long is a question about time. So keeping those units in mind that are part of the problem will help you to make sense of what the question is asking. Right? If they're giving you information about volume, that is V. If they're giving you information about time, that's T. Right? If they're asking you about time, they mean solve for T. If they're asking you about volume, it means solve for V. So there's actually when you keep those things in mind, these problems become much easier. All right, so here we're finding T. So 13 is equal to 0.1, which is 0.5 being a half T. So 26 seconds. And when units have, or when quantities have labels, say what the label is at the end. So the answer is not 26, right? The answer is 26 seconds. Alrighty. Anything else in this problem? Let me think. What else could we ask about such a problem? Well, I don't like this problem too much because, of course, the volume of a gas changes when it's under pressure or not under pressure. So this problem is completely nonsensical, but there it is. 42, I asked you so 42 is similar to that. 42, that's the one I'm asking you to hand in. A large pond is filled with a garden hose at a rate of 10 gallons a minute. And initially the pond contains 300 gallons of water. So we're talking about volume of water in gallons and a quantity of time in minutes. Right, so you got a garden hose, right? And this garden hose is being used to fill a pond, and the garden hose has a certain rate associated with it, 10 gallons per minute, right? And that's more or less constant. So 42, very similar to 41 here. The other problem I asked you to hand in was what? In this section. Oh. I think I got my notes in the wrong order here. So the other problem in this section, I asked you to hand in 2.4, not 2.4, 2.5, it's number 46. So that's a question about time and speed again. So let's take a look at something like that, dealing with speed over time and such. So I've got 2 points, A and B, and their distance apart is 100 miles. Okay, and let's say this is mile 0, this is mile 100, and in the middle is mile 50, mile 25, so on and so forth. I'm going to put a scale. So I've got 2 points, A and B, they're 100 miles apart. Okay, and I've got, so Fran leaves point A going in this direction, traveling at 30 miles an hour. Grant leaves point B traveling at, we'll say 20 miles an hour, 25 miles an hour. In this direction, Grant, 1/2 hour later. Okay, so Fran is going towards B, and then Grant is going towards point A, but Grant leaves a half hour after Fran. Okay, so now the question is, at what time will they meet, and where along this road does that happen? So at what time do Fran and Grant meet in minutes? At what time do Fran and Grant in minutes? So at what time, sorry, in minutes, maybe I should put it here. Do Fran and Grant meet? And where along the road does that happen? Right? Where along the road do they meet, as in how many miles from point A? So at mile 0, mile 50, mile 75, so on and so forth. Okay, before we can begin to address such a question, we will need a distance function for Fran and a distance function for Grant. Okay, so since Fran and Grant leave at different times, the question might be, well, what should be the initial time, the initial starting time? I think I'm going to make the initial starting time when Grant leaves. Okay, but even before that, I'm asking the question, at what time in minutes do Fran and Grant meet? But yet I gave the the speed at which they travel in miles per hour rather than miles per minute. Okay, so first, if we want to talk about t in minutes, then we need to know speed in miles per minute rather than miles per hour. So how do we do that conversion? Okay, well, Fran is traveling at 30 miles per hour. So 30 miles per hour. Right? And for every right, so miles per hour times hours per minute. Miles per hour times hours per minute. If you cancel those quantities in the common quantities in the numerator and the denominator, then you'll come out with units, miles per minute. Right? So to convert miles per hour to miles per minute, you need to multiply miles per hour by hours per minute. Well, what's a quantity that converts so many hours to so many minutes? Well, 1 hour gives you how many minutes? One hour gives you how many minutes?
60.
60. Right? So 30 over 60 is a half a mile per minute. See that? 30 miles per hour, and then there's 1 hour for 60 minutes. So as a fraction, hours over minutes, 1 over 60 is an accurate conversion. Right? So 30 miles per hour times 1 over 60 hours per minute gives you miles per minute, because the common factor of hours on the tops and bottoms of these fractions, they cancel out to give you the units that you want. So similarly for the 25 miles per hour times 1 over 60, hours per minute. So 25 over 60 so 0.416. Let me present it as a fraction. So that's 5 over 12. 5 over 12 miles per minute. Okay, so we have the rates of change of Fran and Grant. Yeah, we have the rate of change. Well, let me take away this part. I don't want to explain that right now. So we have the rates of change for Fran and Grant. Okay, and we also know initially where Fran and Grant starts out. Initially, Fran has gone 0 miles. She starts out at 0 miles. Grant, initially, he starts out at 100 miles. So the distance functions for Fran and Grant are as follows. So Fran, her distance function, f of t, well, she's going half a mile per minute for t minutes, right? So again, the linear function P of t is going to be mt plus b, where m is the rate of change, constant rate of change, and b is the initial condition. So Fran's distance function is equal to half a mile a minute for t minutes plus her initial quantity, or her initial condition, which is 0. So Fran's function is just 1/2 t. Grant's function is what? So Grant is traveling 5/12 miles per minute, but he's going in the opposite direction.
Would Fran's initial condition be after?
Yeah, I'm gonna leave that out for now, just to make the a little bit simpler. So they leave at the same time. Okay, so now Grant's speed is 5/12, but he's going in the opposite direction. So his rate of change of distance, his speed is negative because his distance is starting out at 100 and going down. Fran's distance is starting out at 0 and going up. All right, so Grant, his linear function is minus 5/12 t plus his initial condition. His distance at time 0 is 100. Okay, so Grant's rate of change is negative because his distance is going down. All right, so what time do they meet? What time do they meet? Well, they meet when their distances are equal. So they meet when f of t is equal to g of t. So when 1/2 t is going to be equal to minus 5/12 t plus 100. So let's add 5/12 to each side. So this is 11/12 t is equal to 100. So multiply both sides by 12/11. So t is equal to 1200/11 minutes. So that is 109.09 minutes. So they meet after 109 minutes, almost 2 hours later. So what time do they meet? The other question we're being asked is where along the road do they meet? Where along the road do they meet? Right, so when is asking about, time in minutes. Where along the road do they meet? So now we're asking about distance. Well, we know when they meet, and we know about distance, from these two functions here. So how do I find the where given the when? How do I find the where do they meet, given that I know when they meet?
You solve for distance?
Yeah. So specifically, I do what? I take 109 and put it into either function. 109.09, plug it into either function, you'll get the same quantity. Right? I mean, it's going to have to be either g or f or both, right? Because g and f are in miles. So f of 109.09 is 109.09 over 2, which is equal to right? 54.54 miles. So 54 miles along the road from point A is where they meet. If you wanted to plug it into G, you should get the same answer. Now, of course, we're doing estimations, so it may be off by a little bit. So minus 5 over 12 times 109.09 plus 100. So 109.09 times, 109.09 times 5 divided by 12 plus, well, it's going to be minus in this case, 100. So, well, we were accurate enough. 54.54 miles along the road from point A. All right, so number 46, uses similar ideas to what we're talking about here. So tomorrow I would like to go over this example again, and we'll add back in this business about Grant leaving half an hour after Fran leaves, and we'll talk about how it works in that case. So that's section 2.5. So again, we started talking about lines again, but now we're starting to bring in ideas of physical situations or economic type situations, different sort of situations in which you take verbal information, right, and change it into mathematical information. And that's really where, for almost all purposes, mathematics is interesting. Okay, is where you take information that's verbally presented and you turn it into mathematical information and use the mathematics to solve something about that situation. Okay, that's really where math is interesting for most people. I mean, math is interesting in and of itself for people like me, but that's I'm not most people, and most people are not professional mathematicians. Not that you should be. That's just what I do. All right. Section 2.6. Transformations of functions. So, given the graph of a function, y equals f of x, other functions and other graphs can be obtained by applying standard transformations. Applying various standard transformations. So the first one is about shifting vertically. Shifting a function vertically. By that we mean the following. So here is a function, the standard parabola, but I mean whatever function you might have. Let's just start out with the parabola because it's a fun example. So here is the graph y equals f of x. Here's the x-axis, here's the y-axis. Now, if c is a positive number, actually let me change the color of that. If c is a positive number, all right, and what I do is I add c to f of x, then what I've done with the graph is to shift it upward like this. So this red one is y equals f of x plus c, where c is positive. Right, because all I did is I took the y values of the current graph and I added c to it in each case. And why does it look a little asymmetric there? I guess what I should do is move that over. Yeah, that's better. Of course, I could also subtract c and shift the thing downward. So let's make that one blue. So this is y equals f of x minus c, where c is bigger than 0. So adding c takes the graph of a function and shifts it upwards, right? Subtracting c shifts it downwards. So in this picture, what we actually have minus c, what we actually have is, right, this is the graph y equals x squared. And if I say this is 1 and this is minus 1 here, this is y equals x squared plus 1. This is y equals x squared minus 1. So that's shifting vertically. What if we want to shift horizontally? Shifting horizontally, let me again use this, but so again, this is the graph y equals f of x. If I want to shift it, now I've shifted vertically. Now I want to shift horizontally. So instead of going up or down, we want to go right or left. Well, how does that happen? So this is the graph, the black one, y equals f of x, and this is c, and this is minus c. The red one is f of x minus c. So it's kind of the opposite of what you might suspect. Right? So you want to subtract c from x to shift to the right, not add. Adding shifts it left. So this is the graph, the blue one, y equals f of x plus c. So we're adding c to x, not adding c to f. So in this specific example, now why is it that you subtract? Why is it that you subtract to shift right rather than add to shift right? And why does adding shift left? Well, in this example that I've drawn, this function touches the x-axis at x equal to 0, right? At x equal to 0. So when the argument of this function is 0, we touch the x-axis. The y value is 0. Well, where is the argument of this function equal to 0? At positive c. Not at negative c, at positive c. When I plug in positive c, well, I get f of c minus c, which is f of 0, right? So I get a y value of 0. So I'm touching the x-axis. Similarly here, x plus c, when is x plus c equal to 0? Well, at negative c. Okay, so that's why we get shifted left when you add c, because it takes this point where the argument is 0 and transfers it over here. So, for example, if this black function is y equals x squared, and then this is, say, 1 and negative 1, 1, 0, negative 1, the red function is y equals x minus 1 squared. So that's y equals x squared minus 2x plus 1. And the blue function is y equals x plus 1 squared. So that is y equals x squared plus 2x plus 1. Okay, so adding 1 to the function x squared shifts up. Subtracting 1 from the function x squared shifts down. Subtracting or adding 1 to x, which gives me x minus 1 squared or x plus 1 squared, shifts respectively left and right. Okay, all right, 10:58. So that's all for today. Don't forget the assignments that are due tonight. If you have any questions, you can email me about them. And other than that, have a good evening, and I will see you on Monday.